Assalamualaikum and good days to TS Nizam as the panel for this project. So first of all, I would like to introduce myself. So my name is Norezati Binti Dagang. So I'm from 3BM. So today I would like to present about my final year project 2, and my title of research is to study on effective hardware communication approaches for online monitoring of chiller TCU for the ATM system. Okay, so this is the outline that will present throughout this presentation. So the first one is a project background. The second is problem statement. Third is objective. Fourth is scope of work. Five, technical review. Six, methodology. Seven is the result analysis, and the last one is conclusion. Okay, so next we move to the chapter 1, which is introduction. Okay, first of all, I would like to introduce about this. So this is a simple introduction about the TCU4080. So the TCU4080 is a single channel temperature control device designed for remote heat load temperature management. So the TCU4080 can reduce the heat load produced by the process equipment at a distance up to 50 feet. So the coolant cycle through the TCU4080, where it receives the necessary cooling or heating, is delivered to process equipment, and then it return in a closed loop. So with a tolerance 1.0 degrees Celsius, the temperature control unit 4080 keeps supply coolant at a temperature between not less than 40 degrees Celsius and not more than 80 degrees Celsius. Okay, next we move to the project background. So this study aims to investigate effective hardware communication approaches for online monitoring of chiller TCU4080 system. So chiller TCU4080 system play a crucial role in various industrial applications, such as maintaining precise temperature control in manufacturing process. However, the lack of real-time monitoring and communication capabilities can lead to inefficient operation, increased energy consumption, and potential equipment failures. To address this challenge, this study proposed an online monitoring system using the industrial Internet of Things IIoT system by evaluating different hardware communication approaches for online monitoring of the TCU4080 cooling system. So the study focused on selecting appropriate sensor, communication protocol, and data transmission method to enable real-time monitoring of crucial operational parameters, including temperature, pressure, flow rate, and energy consumption. So various hardware communication approaches such as a wired and wireless solution are analyzed and compared in terms of reliability, scalability, cost effectiveness, and compatibility with existing infrastructure. As a result of this established system, it will provide insight to choose the most appropriate communication solution based on the needs and constraints of a particular application. So implementing this approach can increase operational efficiency, reduce energy consumption, and improve equipment maintenance and reliability in the TCU4080 cooling system across various industrial sectors. Okay, next we move to the problem statement. So the main issue in this project is that staff are having problem to attend manual monitoring and inspection tasks for front panel verification as well as coolant level monitoring, which take time. So by monitoring the system in real time, IIoT device can detect inefficiencies and provide insight on how to optimize performance. So this can lead to time saving and increased productivity. Additionally, physically checking the coolant will only allow us to see the damage on the front panel, which will take time and make it impossible for the support team staff to determine what caused to the damage to the chiller. So with this method, it will make it simpler for the SFT to record data analysis, and it will also make it simpler for the sub-prep team to produce the report on a weekly or monthly basis. So we will be able to assist the SFT indirectly in resolving the issues. Okay, so this is the project objective. So the objective of the study on hardware communication for Chile TCU4080 online monitoring system, the first one is to help solve the problem of sub-prep team staff to conduct monitoring or inspection activity from weekly to monthly, as SFT staff can monitor the status of cooler via the web or mobile for better workforce efficiency. So the second one is to prepare decision matrix criteria for choosing suitable hardware, TCU4080 chiller, IoT integrated monitoring system. And the last one is to analyze the suitable hardware for monitoring indicator light and water level at the chiller TCU4080. Okay, next we move to the scope of project. So this project is developed only limited to sub-fab team, which is aimed to help them in monitoring the status of the cooler, which is only limited to digital signal, and it does not include analog value readings. So based on this project completion, the hardware that is appropriate for this project will be compared and studied for this project. So at the conclusion of this investigation and comparison, a decision on this project will be taken in light of the findings. Okay, next we move to the chapter 2, which is technical review. Okay, basically this technical review is more about spec machine, tool, SOP procedure used in the industry. So firstly, the name of this product is Edward High Vacuum Model 4080 Temperature Control Unit, TCU 4080. So the TCU4080 is a single channel temperature control unit engineered for temperature control of remote heat loads for distance up to 50 feet. So the TCU4080 can cool the heat load generated by the process equipment. The coolant circulates through the TCU4080 where it is cooled or heat as required. Then is transferred to the process equipment and returned in a closed loop. So the TCU4080 maintains supply coolant at a temperature between not less than 40 degrees Celsius and not more than 80 degrees Celsius. So procedure to power up the TCU4080, the first step is ready light should be on. Then we press the reset. The third one is press to start, and the last one is verify that the coolant pressure gauge located on the front access panel are read less than 100 pound per square inch gauge do not to exceed the normal operating parameters. So the system is designed to operate from not less than 40 degrees Celsius and not more than 80 degrees Celsius. Okay. Next, we move to the TCU4080 components. So this is the overview of the TCU4080. So if you can see to the figure, we have around 23 components inside the TCU4080. Okay. This is the component inside the TCU4080. So the component is the first one is reservoir. The second one is a level switch. Third is compressor. Four, crankcase regulator. Five is suction service valve. Number six, discharge service valve. Number seven, temperature switch. Number nine is condenser. Number 10 is a filter dryer. Number 11 is the safety cooling valve. 12 is motor. 13 is pump. 14 is bypass valve. 15 we have hot gas bypass valve. 16 we have a subcooler. 17 solenoid valve SB2. 18 is solenoid valve SB1. 20 thermostatic expansion valve. Number 20 is a heater. Number 22 is a flow switch. And the last one, we have a heat exchanger. Okay, next. This figure is show the front panel components. Okay, for front panel control, what we have is power on, reset, emergency off, start and stop, alarm, and mute. For the temperature controller equipment, we have a process valve, a PV. The second one is set point value. The third one is push button, and the last one is remote mode LED. So for front panel LED indicator, so we have around 9 LED. So the first one is for facility power. So the second one is facility water. Third we for circuit breaker. Fourth for compressor. Five for coolant temperature, and six is for coolant flow. Seven we have for coolant normal level. The eighth coolant low level, and the last one is remote RTD. Okay, so next we have electrical rear panel. So this component is behind of the TCU 4080. So what we have in electrical rear panel. So the first one we have component J7 to J3. The second one is CB7 24 VAC. Next we have a CBS 24 VDC. Next J7 to J2. The number 5 we have a CV4 reservoir heater. Next we have a CV3 circulation pump. Okay, so next we have a CB2 compressor. Next we have a CB1 manpower. So the next one is a normal overfill. So after that we have CB1 manpower. Then we have the normal overfill. Low force. V 200 and 200 at VAC 3 pH. Main for main input power connector. Next we have a CB5 XFMR, and we have CB6 PCU, and the last one is J7 to J1. Okay, so next we move to the chapter 3, which is methodology. Okay, so this is the flowchart for this project. So we start this project with do a literature review based on past projects that have been done. So next step is we do the study existing communication system on TCU 4080. So next we explore the hardware that meet requirement in the latest market. After that we proceed to collect data for this project if suitable and meet the requirement from the management. We proceed to do the result analysis and comparison between the data from the data collection. If not meet the requirement and the spec, we back to the data collection again until it meets the requirements. So the next step is we continue this project with do the documentation, discussion, and conclusion. Okay, so next, this is the research area for this project. So totally, we have 98 chillers on site. So for now, we only proceed to monitor one chiller for pilot project only, and we'll continue the balance after the first project success. So this project is implemented in subfab area for subfab team. Okay, so This is the first condition to monitor. So the first one that I brought in the figure is the indicator light. So as we can see, there are 9 indicator lights. Each indicator light will present two conditions, which is green and red color, to show whether the system is in a good condition or not in a good condition. The second figure is the temperature controller. It's referred to TCU 48 temperature that cannot exceed the set temperature. Okay, so next we move to the condition 2. So this is the second condition to monitor. So which is the coolant level. So actually before this, sub-PEF team only use a manual method to monitor the coolant level, which is by using a cable tie where the coolant level cannot be less than the set level. So basically, for now on site we have three type of coolant level. The first one is HT110. The second one is Florinet. And the third one is Option SF10. So um, all the coolant have the same function, but SFT tries various coolants to test the effectiveness of the coolant. Okay, so next we move to the component used in system layout 1. So what we have here for component system in system layout 1, the first one is a photoelectronic distance sensor. So the second one is Ethernet switch. Next we have I/O link master. Next we have Monio software, and the last one is I/O link module. So the first one is photoelectronic distance sensor. So this sensor is an optical sensor that continuously detect the distance to an object and generates output signal based on the parameter setting. It uses a laser diode as a light source to create a light spot, so allowing for the measurement of distance between 25 to 300 mm. So the sensor also determines the reflectivity of the target object, which is suitable for monitoring and detecting sensor soiling. Second is the Ethernet switch is an unmanaged switch designed to facilitate the connection and communication of multiple devices within a network. As an unmanaged switch, it does not require any configuration or management, making it easy to install and use. So the ALT for the AL3050, which is Ethernet switch, is it store and forward mode of operation. So next we have Monio software. So the Monio is combine the level of operation technology with the level of information technology. So the sensor data generated in the production plants can be read and processed easily and used as a basis of sustainable corporate decision. So the last one we have Monio software. Monio software is has a modular structure and consists basic software as well as application. Okay, so next, this is the component used in system layout 2. So the first component is a float sensor. So the float sensor is a type of sensor used to detect the level of liquid in a container or tank. It consists of a float that rise or fall with the liquid level, and this movement is used to trigger an electrical signal. So next, we have a visual network service in the Microsoft Azure cloud platform. So VNet allows you to create a private network in the cloud that can be used to host virtual machine, web application, and other cloud-based resource. So VNet can be interconnect with each other and with one premise access a network using Azure, Express Route, or VPN gateway. So the third one is a PLC backup. So PLC backup is a PC-based automation system from backup automation. So it is a complete automation solution that includes hardware, software, and engineering tools. The PLC backup system is based on TwinCat automation platform, which provide unfight framework for all automation tasks. So last component is the VBox cloud database. So this cloud is based a database system that allow user to access their data from anywhere in the world. So it is based on the open source VirtualBox visualization software. Um, which allow user to create and run virtual machine on the computers. Okay, so this is the component used in system layout tree. So the first component used in the system is a capacitive sensor. The capacitive sensor are type of proximity sensor used to detect the presence or absence of an object or change in its position without a direct physically contact. So this sensor works based on the principle of capacitance, which is the ability of a system of conductors and insulators to store an electric charge. So the second component is a Zeeman PLC. So the Zeeman PLC or programmable logic controller is a digital computer used to automate industrial process. So PLC are used to control machine and device and to monitor and record data. So they are used in a wide variety of industries, including manufacturing, automation, and transportation. And the last component is SCADA, WinCC, which is supervisory control and data acquisition, WinCC. So it's a popular and powerful human-machine interface (HMI) and supervisory control and data acquisition (SCADA) software developed by Zeeman. So it is used to visualize and control industrial process in real time. So the WinCC is part of the semantic HMI, human machine interface. So product family by Zeeman, which is widely used in various industry for process visualization and automation. Okay, so next we move to the comparison between system layout. So based on the research that has been carried out, a comparison between layout system has been made based on the hardware that will be used in this project only, not in general. So there are several factors that are taken into account in making this comparison. Among them are the factor of modification, connection, installation and maintenance, and the last one is cost. So for system layout 1, no modification. For connection is wireless. For the installation and maintenance, I use plug and play. For the cost is cheaper. So for the system layout 2, for modification, just need minor modification. For the connection, wired. For the installation and maintenance, complex setup procedure. For the cost is more expensive. So for the system layout 3, for the modification, just a minor modification. So for the connections wired, for installation same like system 2, complex setup procedure, and for the cost is yes expensive. Okay, so this is the specification of this project. So all decision and evaluation will be based on the perspective of management. So management has set the specification as a guide in this project. So everything in this project we must have to follow this specification lah. Okay, so next we move to the chapter 4, which is result and analysis. Okay, so this is the decision matrix. So to get result in this research, in addition to doing research from the past project and making comparison, so there is another method that also help in making an effective hardware selection to be applied, which is the decision matrix method. So this decision matrix is a form where the management team will evaluate the effectiveness of each hardware, whether it meets the specification that have been set or not. So the highest score resulting from the matrix decision will be selected as the system that will be applied for this project. Okay, so from the grand total from the decision matrix, I convert into the pie chart. So as we can see here, the component used in system layout 1 is the highest score, which is 69 score. The second one is the highest is component used in system layout 3, which is 53 score, and one is component used in system layout 2. So from the grand total score, management decide to choose the highest score, which is from the component used in system layout 3, due to the system meet the requirement from management. So okay, so there are few videos show here. So the first video is from component used in system layout 1. So this video is present pre-testing of the hardware that will be applied to the future of having a project where this hardware is based on the choice from map from the decision matrix. So this hardware is from component in system layout 1. Okay, next, this second video is also show how this software works, how the software show the response from the sensor that detects code that after the input position of the chiller that has been set up in the software until the report can be converted to Excel. Okay, so next, this figure is show the system architecture for the system monitoring, choosing from system layout 1. So the system is use hardware from system layout 1, like I mentioned. So the component used in the system is the first one is I/O link module, the second one is I/O link master, then the third one is electronic level sensor, and the last one is the monitor software to monitor the outcome and record the data. Okay, so next we move to the conclusion. To summarize, this research is successfully achieved to the objective of this research based on the result and analysis that has been met. So there are three objectives here is the first one is help to solve the problem of subtract team staff to conduct monitoring or inspection activities from weekly to monthly. SFT staff can monitor the status of fully via the web or mobile for better workforce efficiency by the end of September 2023. So next is to prepare decision matrix, criteria for choosing suitable hardware, TCU4080 chiller, IIoT integrated monitoring system. And the last one is to analyze the suitable hardware for monitoring indicator, light and coolant level at chiller TCU4080. So next we move to the limitation of this project. So the primary limiting factor for this study has been the rather constrained time frame within which it had to be executed. So the disparity between the university schedule and the company's project timeline has been a critical issue. So consequently, this project has been successfully complete only up to the stage of selecting the optimal hardware component for implementation. To achieve its full potential, this project would require a more extended the timeline. Looking ahead, it is imperative to consider aligning university project scheduling more closely with those of the partnering companies to allow for comprehensive exploration uh, such project and ensure their successful completion in the future. Okay, so for the last part in this project, so for future work and recommendation, so management suggests and hope this system can focus for condition monitoring to reduce cost saving in the future. So the second one, management hope system can view the condition chiller status via phone. For now, this project only can monitor this status via PC or laptop only. So the last one is can management hope the system can expand for 97 unit more chillers balance for the picture lah. Okay, I think that's all from me for this presentation. Thank you for TS Nizam. Okay, I think that's all. Thank you.